This
Theo,
transition.
tell me when we're live.
We are live, Heather.
Good evening, and thank you for joining us for another Tennessee Virtual Star Party, which is hosted by Warner Park Nature Center, a metro park in Nashville, Davidson County, Tennessee. And we're going to take you tonight across the state of Tennessee, beginning in Kingsport and going all the way to Memphis. We're going to have some stops along the way. We're going to stop and listen to the story of the drinking gourd. We're also going to listen to a couple of sounds that you might hear once you're able to get outside in late February. My name is Heather Gallagher. I'm a naturalist at Warner Park Nature Center, and I'm joined again by friends from across the state. Adam Vans from Bays Mountain Park in Kingsport, Dr. Billy Teets from Vanderbilt's Dyer Observatory, my friend Theo Wellington, who is one of the spokespeople for the 2017 solar eclipse, as well as a member of Barnard Safert Astronomical Society, and my friend Ann Viano from Rhodes College, and she has an observatory there as well in Memphis. We are all going to be available throughout this to answer questions. We're going to share our screens across the state. I especially want to thank Friends of Warner Parks for providing this Zoom space for us. Friends of Warner Parks is a 501c3 in Nashville, Tennessee, that has provided millions of dollars in funds, not only for the preservation of the 3,200 acres of Warner Parks, but also education and just so much staffing, information for not only the people of Nashville, but for the millions of visitors that come to Warner Parks every year. I look forward to sharing this with you. We're going to start in East Tennessee in Kingsport, up in the northeast corner, with my friend Adam Vans from Bays Mountain Park.
Alrighty, I guess I'm on. Hello, everybody. My name's Adam Fans. I'm the planetarium director at Bays Mountain Park and Planetarium in Kingsport, Tennessee. And I'm actually at my house right now, and it is cold. We're all cold, but I seem to be one of two that are actually outside. So what we've got here tonight is actually a really great mix of content from all of us, all five of us presenting tonight, and I think you're going to really enjoy it. Well, right now you're seeing me, and you're seeing a little image of a logo, and I wanted to kind of highlight that logo real big and real bright, and I'm in the corner. This year we are celebrating our 50th anniversary at Bays Mountain Park and Planetarium in Kingsport, Tennessee. And if you don't know, Heather actually was a naturalist there at the park 21 years ago. So, yeah, she doesn't show the age. She's saying don't talk anymore about that. But anyway, of course, the pandemic makes it hard, but at least we're celebrating in spirit. And we will have things planned later on, especially once we are all able to be together and gather and have a lot of fun. But I at least wanted to plug that, our 50th anniversary. So what am I going to be doing right now? First of all, let me show you this image right here. So now you're going to see me as a small little circle on the side with our official logo, and you're going to see a circle of the sky. And this image is the entire sky. So you are seeing a bunch of stars, and then very faintly you're seeing some constellations in the background there. And that was on purpose. They're just very subtle. Now, if you look in the dead center of that circle, that's what we call the zenith, the point straight above your heads. So it's right over your head is that center point. If you are facing the south, then you see the S, the little red S on the bottom there. So if you're facing the south, that area of the map is where you would be looking. If you were looking to the west, you could either kind of turn your head to the right or look to the west and then rotate this chart so that the western part, that right part of the chart, is down in front of you, and so on for east or north. Right now we're facing south. If you look about halfway up between the horizon and the zenith, you are seeing a constellation that's very famous. I'll talk about it in a few minutes, and we have some others that will be talking about it as well, and objects to see, and it's the constellation of Orion the Hunter. And you're going to see what looks like a little hourglass shape. 4 stars that makes a rectangle with 3 stars in a row, making the belt of Orion. And that is Orion the Hunter. And I was going to talk about what's called the winter hexagon. So I want to show the drawing first, this drawing. Then I have a camera showing the actual sky. It is clear out right now, but the first quarter moon is up, and so it's kind of washing the sky away. So you see Orion. If you look to the bottom right of Orion, you see a white star there, and that is Rigel. And the winter hexagon is 6 very bright stars of the winter sky. So we'll start with Rigel, the white star. We're going to go straight up a little bit, close to the zenith, and it's kind of a red star. That's Aldebaran, the fierce red eye of the bull, of Taurus the bull. Then when you go really close to the center of the picture, remember that's called that's right, the zenith. You're going to see another kind of a bright white star, that's Capella. Then you're going to go down and to the left some. You're going to see 2 stars near each other. Those are the heads of the twins of Gemini, the twins, Castor and Pollux. Go straight down a little bit. You're going to see a white star called Pollux. Go down again and slightly to the right, and it's the brightest star in the entire night sky called Sirius. And I know you're going to be seeing that star later on too. So if you go around, it makes this big hexagon. All right, so here what I'm going to do, I'm going to show you a cheat sheet. There you got our hexagon. Can you see? So on the bottom is Sirius, then to Rigel, which is the foot or the knee of Orion, up a little to Aldebaran, which is in Taurus the bull. Up towards the center, the zenith, is Capella. Down and to the left a little is Castor and Pollux, those 2 stars near each other. Down some is Pollux, back down to Sirius. Now, here is the actual night sky with my camera. You can see the moon really bright, and I do have a green laser pointer, but it's still not bright enough to compete with the moon. So near the very bottom of this, so you see me on the side, kind of in the center of the image, go down, and the brightest object, that's Sirius. And then as you go up and to the right, you're going to find the red star Aldebaran. Keep going. Then you find Capella, and the other stars are faint. I apologize, it's not the best image, so we are going to go back to this one. So at least we did have a live view of the winter hexagon. Now, I'm not done because I wanted to cover a couple of other neat things. And so there is Orion that we talked about, and it's higher than what I pointed out, that hourglass shape, because his right arm is up over his head and he holds a club over his head because he's battling Taurus. Now, Orion's going to come up later with, I know Billy's going to talk about it, and I think others will too, but let me continue a little because we're going to talk a little bit about some star lore about Orion. Okay, so Orion, now here I've zoomed in on the bottom part of the chart, and now you can see Orion the Hunter. He is battling Taurus the bull. I don't think I need to describe it. You can see him. And then next to Orion are his 2 faithful companions, Canis Major and Canis Minor. So we're going to get into a little bit of, I know there's terminology, there's a name for this terminology, but the Latin names of animals. So the species, I believe, Heather, shake your head yes or no. If it's Canis, that's correct. Okay, so that's a species. So Canis means dog, and you can see that, or canine. And major and minor, I think you can figure that one out. Big and little. So we have the big dog and the little dog. And Sirius, the brightest star in the entire night sky, is in the collar neck area of the big dog, of Canis Major. This is the Greek story. I don't want to go too long because I don't want to take up other people's time. But our culture and modern day culture around the world sees these pictures, which are Greek in origin, from Greek mythology. But there's lots of cultures in this world, especially the star lore from ancient times. Now, you probably notice some of the star names sound a little different or a little unusual. Well, Aldebaran and Sirius, and there's Rigel and Betelgeuse. Those are all ancient Arabic in origin. They were not the first to name them. They were just the first to write them down and have a written record. That's why those names have stuck. But this is the Greek culture view of the winter sky, with Orion the Hunter and Taurus the Bull and the two dogs. But wait, there's more. What if you were ancient Egyptian? You would see Osiris. Notice the difference. You see Orion. I did not change the scale, but Osiris is enormous. His crown are the 3 stars of the belt plus Betelgeuse, the red star. That's his whole crown there. And then his body extends all the way down to basically the horizon. So he's enormous in the sky, and it's just one picture, the Osiris. So that's the ancient Egyptian view. And of course, each culture has different environments which will determine what they see. So in Egypt, now this is based from one of our planetarium programs that we produced called A Part of the Sky called Orion. And so we have 2 different cultures seeing this, but think about it. You know, Greece is in the Mediterranean. Egypt is in more southerly climes and is in desert land, and so you have sand and camels and stuff. But our third culture is the Inupiaq, and you may not have heard of that term. They are part of the Inuit, which is the proper term for what people call Eskimo, but Inuit is actually the correct term to use. It's the proper term, and Inuit is the general term of all Native Americans that live in, the very, I bet you can guess, northern areas, northern climes, north of Canada and Alaska. And so what's it like there? Colder than here. Even though it is cold, it's colder there. And they have a lot of snow and stuff. So they're not going to see deserts or pyramids or camels even like the Egyptians did. They saw polar bears, which can only be found in the northern area, in the Arctic. Now, it's a little hard to see. They're really tiny. No fear. I've got a bigger version. So now you see Orion the Hunter. You see in the belt stars of Orion 3 Alaskan Native Americans. They are the Inupiaq, which is, again, a small subsection, a tribe of the Inuit, which is all peoples that live there. And then if you go up, you see the red star Aldebaran, and it has a picture of a polar bear, and that's Nanook. And you may have heard of the story of Nanook of the North. That's Nanook, the polar bear. And I know it's small, but next to Nanook are 5 wolves. Can you see the face of Taurus the bull, that V shape, where you have the red star Aldebaran and then the wolves? It's kind of a V shape, those other stars. This is interesting because they did not make a picture with a bunch of stars, they have individual stars for pictures. I should put it that way. So Nanook is one star. The 5 wolves are 5 stars. They're hunters actually, are the 3 stars of the belt. So they don't have giant pictures made up of a bunch of stars like a dot-to-dot picture. They have individual stars for individual pictures of characters within stories. And so this is the Inupiaq story of Nanook of the North. And so basically Nanook was looking for food and was being attacked by the wolves, but the 3 hunters kind of saved the day and scared off the wolves. And so that story is celebrated by being placed into the sky. And then I know Thea's going to talk about this, so I'll just point it out very briefly. Just to the upper right of Nanook and the wolves, you see that little cluster of stars? That is the Pleiades star cluster. She'll be talking about that later. So here we are back to our full sky, and I'll put this back onto me. I'm going to stop right there because that's my 15 minutes right now, and I'm going to give it back to Heather. So I hope you go out, look to the real night sky. Tomorrow may be clear. Go out, look for Orion. It's super easy. It's in the south. You'll find it. Okay. Thank you.
Thank you, Adam, so much, and so exciting to see you again. I am really pumped to introduce someone who has continued these Tennessee virtual star parties over the last year. Dr. Billy Teets, my friend from Vanderbilt University's Dyer Observatory.
All right. Well, thank you very much, Heather. And Adam, I learned a lot there. So thank you for telling us about the winter hexagon and the stories from the different cultures. So always learning something on these, even though I'm a presenter, and that's one of the reasons why I love doing these. So as Adam had mentioned before, I'm one of the others that's outside, although it looks like Dr. Viano is outside as well, but she doesn't look too cold. But yes, I am actually out in my driveway. So I'm the director of the Vanderbilt University Dyer Observatory. And so we would normally be doing these, or I would be broadcasting from the observatory tonight. However, the road going up there is still really treacherous, so wasn't going to risk that, especially after sundown, and then the ice is starting to form again. So before all that, I had brought one of the portable telescopes home so that we could possibly do some viewing, and thankfully it cleared out for us. So we're going to do a little bit of viewing tonight. So a little bit about the observatory. If you haven't been there before, please check out our website. It's dyer.vanderbilt.edu. Unfortunately, we can't do any in-person events right now, but as Heather was saying, we're still continuing to do our virtual events. So please check out our calendar there. We've got some other resources online as well. So like I was saying, I am actually out in my driveway right now. I have one of the telescopes set up, and being in my driveway, there's been some traffic going back and forth, so you may hear a little rustling in the background as cars pass by, but I'll try to make sure to talk a little bit louder if they do pass by. Haven't had anybody stop and ask me what I'm doing out here yet, but we'll see. We may get that. So the topic for part one of my presentation tonight is a star that you probably heard a lot about, but maybe not seen or realized that you were looking at that. So Adam had mentioned the star Sirius, which, as he mentioned, was also the brightest star in the night sky. But the star that we'll be looking at is often mistaken as being the brightest star in the night sky. So let me do a quick screen share. Let's see. And we should... That worked. Yes. Okay. Can you all give me a thumbs up if you see the star? All right, thank you. So we are looking not at the brightest star in the night sky, which again is Sirius. We are looking at the star that is typically referred to as Polaris. and one of its other common names is the North Star. So as you can imagine, the telescope is looking north. In fact, it's looking pretty much exactly due north. So normally, when we're looking at stars through a telescope, we have to, if we especially want to watch the stars for a period of time, and examine them closely, or whatever we happen to be looking at, we want to be able to examine for maybe a minute or so or whatever. We have to have our telescope actually following those objects across the sky. Because if you've ever been outside, as said over in the west, the stars, the planets, everything guide does the same thing. Now, the telescope that I'm using right now is looking at Polaris. That's the bright blob that you see right in the center of the screen. But surprisingly, I don't have the telescope running right now. It is sitting perfectly still. But you notice that the star really isn't moving across the screen. And that's because Polaris is notable because of its position in our sky. It's so close to the point in the sky where everything appears to rotate. That point is known as the celestial pole. It's so close to that Polaris, over the entire 24-hour period, the time it takes the Earth to rotate once, it makes just a really, really, really tiny circle in the sky. It doesn't make anywhere near a large circle as what we see everything else doing. So as a result, Polaris is moving very, very, very slowly in our field of view right now, which is why I didn't have to worry about setting up the telescope to track Polaris like I would any other object. Now, if you take a look at Polaris, you'll notice a couple of things. First off, you'll notice that it looks like it's kind of flaring. It's doing this shimmering effect. So that shimmer is purely an effect of our atmosphere. If we did not have air above us right now, or the telescope was out in outer space looking at this star, that star would look perfectly still. It wouldn't be shimmering at all. But because as air is moving above us and the light is traveling through that air, there are different layers of different temperatures and densities, that light kind of bounces around a little bit. And that causes the twinkling that we normally see on stars. It may look really pretty, but when you're trying to take an image, especially if you're trying to pick out little details in an image, that shimmering or that twinkling effect blurs the images. So it looks pretty to the eye, but if you're trying to do images or do research, as professional astronomers do, the shimmering is really a pain in your side. But there are ways to kind of counteract that as well. But there's one thing I want to point out here. You'll notice Polaris, that bright blob there, but now look over just to the edge of it, and you'll see something else. There's another little star there. If you have a telescope set up and you have moderate magnification, you don't have to have a huge telescope, but a medium to larger telescope helps. You can actually see that the North Star is not one, but it's actually two stars. So what you see with just your eye is what we call Polaris A. Okay, so many stars in our night sky are double stars or triple stars or even more stars. So the brightest of those we give it the letter A afterwards. Okay, so the bright star here is Polaris A, and then our little star over here is known as Polaris B. Okay, so Polaris B was actually discovered in the year 1779 by a very famous astronomer called William Herschel, or actually Sir William Herschel. If you've heard that name, he's a pretty famous guy. 2 years after this, he would discover the planet Uranus, the next planet after Saturn. And he made many other discoveries in his career. And his sister, Carolyn Herschel, also made a lot of discoveries as well. But let me switch over, and so this was a live view from our telescope. And just for reference, it is a 9-inch telescope. So it's a decent sized telescope, but you don't have to have one that big to be what we're seeing here. So you can actually pick those out in a medium telescope. So we see those two stars. That's not all there is to this star system. So let me stop my screen share, and I'm going to switch over to my PowerPoint just for a quick couple slides. Find my PowerPoint, and then share my screen. All right, so now we should see Polaris and how to find it. Is that correct, everyone? Can you give me a thumbs up? Or all right, thank you. So Polaris, if you don't know where it is, it's actually pretty easy to find. Now, if you're in the middle of a really bright city like the middle of downtown Nashville, you might have a hard time seeing it because it's not the brightest star in the sky. It's actually about the 50th brightest star in the sky. So it's not super faint, but it's not. But Big Dipper, it's really asterism. So when we say asterism, we mean a very noticeable formation of stars in a constellation. So these are some of the brighter stars of Ursa Major, which is the Big Bear. But the Big Dipper is not itself a constellation. It's part of a constellation. So again, what we know as an asterism. But you can find those bright stars of the Big Dipper, and go to the N2 stars, connect those with the line, and they will point right down to Polaris. Okay, so it makes it very easy to find. And it doesn't matter what time of night, as long as you can see the Big Dipper, then it'll point to Polaris. All right, just two more slides here. So Polaris, as we saw Polaris A, and then in the telescope we also saw Polaris B. But that's not the only star that is a companion to bright Polaris A. There's actually a third star. Now, it doesn't matter how big of a telescope that you have in your backyard, you're not going to be able to see that third star. Okay? We'll talk about that in just a moment. This whole star system is about 450 light years from us. So that means that the light you're seeing the next time you go out left that system about 450 years ago, traveling at the speed of light, and it is just now getting there. So it is a trinary star system. Now, we had Sir William Herschel discover Polaris B in 1779, but it wouldn't be until 1929 that astronomers, when they were studying Polaris A and were breaking up the light of Polaris A, that they noticed the signal of a third star. So this star is called Polaris AB, okay? And it's got that capital A because it's right around this guy here, and it's the second brightest of those two. So, but when astronomers were studying Polaris, or Polaris A, they broke apart the light and they could see that there was the signature of two stars in that system, even though they could still only see the one. They knew there were two because of the information that was encoded in the light. Okay? Now, the Hubble Space Telescope was able to image Polaris A, and as you can see here, we got bright Polaris A, that tiny little blip right there. That is Polaris AB. Okay, so we have been able to image it and confirm that it was indeed there. But again, you're not going to be able to see that star. So let me go back here. Well, I think I may have lost my screen share there. Give me 1 second here. Well, it's fine. Well, anyway, the final thing I was going to mention is that Polaris A, the really bright one that you can easily see with your eyes, that is known as a Cepheid variable star. So it's called Cepheid because there's a constellation up in the north called Cepheus. It's the king in mythology. But there's a type of star that was first discovered in that constellation, and that kind of star pulsates. It physically swells up and shrinks down over a period of time. Maybe a few days, maybe over 100 days, depending on the star. So Polaris A is known to be a type of Cepheid variable. And when it pulsates, which I forget the exact pulsation period, it will slightly enlarge, slightly shrink back down over a period of time. And when it does that, it changes its brightness a little bit. Now, it doesn't change it dramatically. You have to have a telescope and a camera to be able to measure that pulsation, but nevertheless, it is there. So there are other types of variable stars. especially up in the northern sky. There's one that you can look up called Algol. It's a different type of variable star, but that's one that if you actually carefully watch it over a few days, you will see that it's changed brightness just with your own eyes. Okay. All right. Good question. So there's a question that popped up. Do Polaris and Polaris B orbit one another? So to answer that question, let me go back in and share my screen one more time, and then I'm going to hand it off here. Share screen, and there we go. Yes, I'm very glad that you guys asked that question, because that was one of the points that you all forgot. So yes, all of these stars, they are orbiting around a point called the common center of mass. If you were to imagine, like if you had two stars, you put them on a seesaw, okay? If you had a bigger star, then the seesaw would go down to the ground with the bigger star. But if you move that balance point just to the right spot, then the little star can balance the big star. And that point is called the center mass. So all three of these stars are going around that center of mass. But because Polaris A is about 4 to 5 times as massive as our sun and about 40 times wider, it's the big guy of that system. So it does most of the just kind of sitting there while the other stars go around. But Polaris B, it takes tens of thousands of years for it to make one orbit around Polaris A, because its average distance is about 80 times the distance that Neptune is from our sun. So what's amazing is that even at that super, super huge distance, the gravities of those two stars are still able to keep them going around one another. Now, Polaris AB, it is much closer. It's about the distance that Uranus is from the sun. So it's much, much closer to Polaris A, so it doesn't take nearly as long. Okay. So let me stop my screen share there and see if there were any other questions. Doesn't look like there are any at the moment, but if you all think of some other questions, I'm more than happy to answer those in the second part, or any of our other presenters are happy to answer those as well. All right. Turn it back over to everybody else. Thank you.
Billy, that was the absolute perfect lead into what we're going to do next. So my friend Adam in Kingsport talked a little bit about Egyptian, Inuit, and Greco-Roman folklore. And Dr. Billy talked a little bit about Polaris, the North Star. And I think we're also later going to talk about the stars that are kind of in the orbit of Polaris, just constantly moving around the North Star. In the meantime, let's take Polaris, let's take folklore, and let's listen to the story Follow the Drinking Gourd, shared by my friend Alonzo Rhodes from Metro Nashville Public Schools. Thank you.
All right, so this has to come out of my screen, so give me a minute here to share that. I think I have it queued up. I'm doing a lot, so it makes me run pokey slow. All right, let's see if this will go. Share. Here we go.
Good evening, everyone. First and foremost, I would like to thank Miss Heather Gallagher for inviting me and giving me the opportunity to share a story that we have both had a chance to cover with our kids on some of our night hikes when I was working with Metro Parks and Recreation. Let me introduce myself. My name is Alonzo Rhodes. I'm a school teacher here now in Nashville at John Early Museum Middle School. I teach physics education. And I just want to share this story. The name of the story is called Follow the Drinking Gourd. It was written by Jeanette Winter. Just a little background, a little note about the story, shared and written by Jeanette Winter. In the earlier days of slavery in the United States, many slaves tried to escape their cruel bondage by fleeing north, usually to Canada, to freedom. By the 1840s, a loosely organized group of free black slaves and whites sympathized, formed a secret network of people and places that hid escaped slaves on their dangerous journey to freedom. A network that came to be known now as the Underground Railroad, which is traveling along the darkened roads at night, hiding out by day, moving slowly on the river along hundreds of miles of connecting waterways. Now, the fugitive slaves had their hardships. Slave catchers hunted them down with dogs, many that were shot, they were even hanged, and even after crossing into free states, runaway slaves still could be captured and returned to their masters for a reward. One of the most famous conductors on the Underground Railroad now has been known as Harriet Tubman, who was a runaway slave herself, who led hundreds of her people to freedom. Among other conductors, there was a one-legged sailor named Peg-Leg Joe. He would hire himself out to the plantation owners and as a handyman. Then he had made friends with the slaves and taught them what seemed to be a harmless folk song. And the name of that folk song was called Follow the Drinking Gourd. But hidden in the lyrics of the song were directions for following the Underground Railroad. The drinking gourd is the Big Dipper, which points to the North Star. When the sun comes back and the first quail calls, meant spring, when travel might be least hazardous. As the runaway slaves followed the stars north, they would come across marks left by Peg-Leg Joe and made in the mud. On the charcoal of dead trees, a left foot and a pig foot, and they would know they was on the right track. The river there ends between two hills, which was the Tom B. Big River, and the second was the Tennessee River, and the Great Big River was the Ohio River. And this is where Peg-Leg Joe will be waiting to ferry them across to the free states on the other side. From there, the fugitives were guided from one hiding place to the next until they luckily they had a chance to make it to Canada or other safe places in the north. That's just a little background on the book. Let's dive into the book. Follow the Drinking Gourd. Long ago, before the Civil War, there was an old sailor called Peg-Leg Joe who did what he could to find and to help the free slaves. Joe had a plan. He'll use his hammer and a nail and a saw and work for the master, the man who owned the slaves on the cotton plantation. Joe had a plan. At night, when work was done, he'd teach the slaves a song that secretly told the way to freedom. Just follow the drinking gourd, it said. When the song was learned and sung all day, Peg-Leg Joe would slip away to work for another master and teach the song again. One day, a slave called Molly saw her man James sold to another master. James would be taken away, their families torn apart. Just one more night together. A quail called in the trees that night. Molly and James remembered Joe's song, and they sang it low. When the sun comes back and the first quail calls, follow the drinking gourd, for the old man is waiting to carry you to freedom if you follow the drinking gourd. They looked to the sky and they saw the stars. Taking their little son Isaiah, old Hattie and her grandson George, Molly and James set out for freedom. That very night, following the stars of the drinking gourd. They ran all night through the fields till they crossed the stream to the woods. When daylight came, they hid in the trees, watching, listening for the master's hounds, where they set loose to find them. But the dog lost the runaway scent at the stream, and Molly and James and Isaiah and old Hattie and young George were not found. They hid all day in the woods. At night, they walked alone. And they walked again, singing Joe's songs and looking for the sign that marked the trail. The river rain makes for a very good road. The dead trees will show the way. Left foot, peg foot, traveling along, follow the drinking gourd. Walking by night, sleeping by day, For weeks they traveled on, sometimes berries to pick and corn to snatch, sometimes fish to catch, sometimes empty bellies to sleep on, sometimes no stars to guide the way. They never knew what lay ahead. There was danger from men who would send them back, and danger from hungry beasts, but sometimes a kind deed was done. One day, as they hid in the thicket, a boy from a farm found them. In a bag of feed for the hogs in the wood, he bought bacon and cornbread to share. Singing low, they traveled along. The river is between two hills, follow the drinking gourd. There's another river on the other side, follow the drinking gourd. On and on they followed the trail to the river's end. From the top of the hill they saw the new path, another river beneath the stars to lead them to the freedom land. The drinking gourd led them on, the song was almost done. When the great big river meets the little river, follow the drinking gourd. For the old man is awaiting to carry you to freedom if you follow the drinking gourd. Then they climbed the last hill. Down below was Pig-Leg Joe, waiting at the wide Ohio River to carry them across. The spirits rose when they saw the old man. Molly and James and Isaiah and old Hattie and George ran to the shore. Under a starry sky, George rowed them across the wide Ohio River. He told them of hiding places where they would be safe, a path of houses that stretched like a train on a secret track leading north to Canada. He called it the Underground Railroad. It carried riders to freedom. The first safe house stood on a hill. The lamp was lit, which meant it was safe to come. Ragged and weary, they waited while Joe singled low with a hoot, woo-woo, like an owl. Then the door opened wide to welcome the freedom travelers. They would rush through the house to the barn, for the farmers knew there were slave catchers near. A trap door in the floor took them under the barn to hide till it was safe to move on. Then Pig-Leg Joe went back to the river to meet others who followed the drinking gourd. With danger still near, too close for ease, the farmer sent the 5 travelers on. He drew a map that showed the way north on the midnight road to the next safe house just over the 2 hills. This time, James called the signal a hoot like a owl, Woo, 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 woo. They opened a door to a Quaker's farm. The travelers were led to a secret room hidden behind shelves. They rested here for many days, and they healed their wounds. They slept in soft beds. They got full off of meals. They received new clothes, hot baths to wash away some of the fear and the pain. Isaiah smiled. When they were strong, they traveled again from house to house on the Underground Railroad. Still following the drinking gourd north, sometimes they traveled on foot, sometimes by cart. Rode near their journey's end, carried fruit to the market, and the runaways to freedom. At last they came to the shore of the Lake Erie. Molly and James and Isaiah, old Hattie and young George climbed aboard the steamship that would carry them across to Canada, to freedom. 5 more souls are safe, old Hattie cried. The sun shone bright when they stepped on the land. They had followed the drinking gourd. The river makes a very good road. The dead trees will show you the way. Left foot, pet foot, traveling along. Follow the drinking gourd. Follow the drinking gourd. Then they would say, the river's in between 2 hills. Follow the drinking gourd. There's another river on the other side. Follow the drinking gourd. Then they will repeat that as part of the chorus. When the great big river meets the little river, Follow the drinking gourd, for the old man is awaiting to carry you to freedom if you follow the drinking gourd. Mind to tell you, I'm not a singer. I was just doing it for you all. But that was the story of Following the Drinking Gourd by Jeanette Winter. Thank you so much. Thank y'all so much for allowing me to share with you all the story of the drinking gourd. Back to you, Miss Heather.
That was really fun. Oh.
Theo, what's going on in Goodlettsville?
Okay, well, we're going to reshare the screen, and we're going to move past Alonzo there, hopefully. Why do I have a 1? Oh, Lord of mercy. Okay, so we're going to move on here to, with a little bit of luck, a view of what the backyard looked like and why I'm not in it. Hang on. Come on. Come on, come on, come on. There we go. So that was my backyard this afternoon. And yeah, not much melting went on, so we're not going to be in that. So instead, though, I did go out last night and set up the telescope on the snow. I just didn't want to sit out there and try broadcasting in the snow. So I did catch a little bit of video last night of the moon. It was a beautiful quarter moon last night. It wasn't quite as clear as they promised, but it wasn't too bad. So that's what the moon looks like in real live life. If I were at the star party, that would be the view you would get through the telescope pretty much. It would actually be slightly clearer than that with your eyeball, but that's pretty good. So, you know, the moon is one of those things that's been with us forever and ever and ever. It was our calendar a long time ago. It really still is our calendar. There's a reason why we have 12 months in a year. And we just celebrated the Chinese Lunar New Year. They still keep count by the moons of when the New Year comes. And numerous religious holidays are actually still connected to the moon. So the moon has been a part of us for a very long time, and it's the easiest thing to explore in the night sky. So this is a still picture, and I went with this so that I could do some fun labeling, because I'm really lousy with like the blackboard function in Zoom. So there are a couple of really easy to spot, even with just your eyes, but in a pair of binoculars, it's really easy to do. Things you can look at and learn about, and I'm just as bad as a lot of people. I really haven't memorized a lot of fun things about the moon. So we're going to start on that big patch that's there on the right-hand side. Right there. It really stands out even from crescent moon on. And it's called Mare Crisium, the Sea of Crises. Now that's kind of a weird name for a spot on the moon, but all of the big dark areas on the near side of the moon were called mare, and that's simply a Latin term for seas. You know, on Earth, big flat areas happen to be seas, and so when people looked at the moon, they said, okay, that's cool, we can do that. It's about 460 miles across, depending on exactly which way you measure the dimension. But it's a really nice, fun bullseye. And these places are actually very, very flat. They're places where lava came up out of the moon's thin crust at the time and just flowed out and made a nice sheet. Some of them are impact craters, or the impact kind of helped shatter the crust, and then the lava just kind of oozed out after that. And we know this partly because we've done a lot of work characterizing the minerals that are on the surface of the moon with various instruments that have been in orbit. So it's kind of fun. Those mare really stand out. I mean, you can see them in that nice, pretty bright pink color. And they're all basaltic lavas. And we also know this because we sampled one. This is the landing site of, I think it was Luna 4, the Russians sent a spacecraft. They didn't get a lot of press. You know, we kind of stole all the thunder with Apollo. And so they didn't get all the press, but they did land and return samples from the moon. So what you're seeing here is a picture from an orbiter that's currently in orbit around the moon. It has an excellent camera, so it can get down with details that we cannot see. And they were interested to find the spacecraft or the bottom of it, because just like Apollo, when it took off, it used the bottom of the lander as its launch pad. But they wanted to find it to know exactly where it landed, so that they knew exactly where the rocks it brought back came from. So that's kind of fun. You can see a lot of little white dots there all over the landscape. Those are thought to be bits of insulation that blew out from the spacecraft when it took off. So that's kind of fun. This spacecraft, by the way, is called the Lunar Reconnaissance Orbiter. And it is just doing a wonderful job of photographing the moon in extreme high details. You can see the bar there at the cross, that's 25 meters. And you can see the really angular shadows from the spacecraft bottom there in the inset at the bottom. So even when you blow it up, there's still quite a bit that you can see. And there are more of those big flat dark areas. So that one right there is the Sea of Serenity. That's followed by the Sea of Tranquility, which you may remember was the landing site for the Apollo 11 spacecraft. And there's the Sea of Fertility. So there's four really easy, the Sea of Crises, the Sea of Serenity, the Sea of Tranquility, and the Sea of Fertility. Now, interestingly, these names were given to these by a gentleman who did a map of the moon back in the late 1600s. About, 60 years or so after the telescope and Galileo first started looking, folks started looking hard and they developed better telescopes, and so they wanted to name things so that, again, everybody would know what you were referring to. So that we had an artist that drew the moon, and we had another gentleman who was responsible for naming things, and a lot of his names stuck. And at the time, the moon, when it was in its early phases from crescent up to first quarter, was associated with good weather, with nice things. And so all the mare on this side of the moon's front surface have names like Serenity and Tranquility. They're happy names and fun names. If we were in the other quarter, the last quarter moon, the mare when the other side comes into view for up to full moon, those are all like the Ocean of Storms and, nasty sounding weather names. So it's kind of interesting that that naming scheme still survives to this day. So we have a few landing sites. So there's Apollo 11. These made nice places to land. They're flat, they're safe. There's where Apollo 15 landed, Apollo 16, and then Apollo 17. So there were where a number of our Apollos landed. And again, we picked the nice, flat, easy to get to, safe places. We didn't want to land on a crater edge or something like that. And if you're interested, so one of the perennial questions we get is, can you see the flag on the moon that the astronauts left? And the short answer is no, not from here. We're 250,000 miles away. You can see on the scale there that the Sea of Crises was 400 and some odd miles across. You can't see detail that fine. If you get a telescope that is something like, I don't know, what was it, 600 feet or anyway, a huge telescope, then maybe, but we don't have even telescopes that big on the planet. So the easy way to do it, though, is that you send an orbiter to the moon with a good camera like the Lunar Reconnaissance Orbiter, and you take pictures from there. This is the Apollo 11 landing site. Now, Buzz Aldrin reported that when they left, the flag blew down. So we don't actually see the flag, even with being right there in orbit for this one. But we can see some of the other things. There's the bottom of the lunar module that got left behind, some of the instrumentation. And you can see some of the tracks they made walking around as well. Now for this one, which I think was Apollo 17, yeah, it's up there in the head, we can see the flag, but you have to be right there at the moon. So they took this picture very deliberately when the shadows would be long, because that makes the stuff on the ground really pop out. And they knew that the flagpole, if it was still standing, and the flag then would cast a shadow. So that's what they did, and they got a nice shot of it there. So you can also see some of the other tracks. LRV was the lunar rover. They left it parked a distance away with the camera turned on so that they could watch the astronauts blast off. So that's kind of fun. They had to guess a little bit about the slew rate. We didn't have the kind of control software we might today. And also, even for the moon, it's a 1.5 seconds or so delay, so it's hard to do things with a joystick on Earth in real time. But they had a pretty good guess about how fast they needed to slew the camera to watch the takeoff. So that's kind of interesting that you can see that stuff. It's just that you have to be there. Now, maybe someday some future tourist will go to some of these places. They're actually already trying to consider what happens if we have people on the moon and somebody wants to go take a trip over to one of these sites. Is that a World Heritage site and you may not disturb the footprints? No selfies next to the lunar module? What kind of rules are there going to be for future tourists on the moon? But surely at least one will have a place where you can stand, because you would want to do that if you were there, and take a picture. It'd be fun to know what the flag looks like today. There's a lot of speculation that ultraviolet light has basically bleached it, and it may have a lot of puncture holes from micrometeorites going by. Every little tiny rock that hits the moon leaves a mark. There's no atmosphere to slow things down. And eventually that pummeling will eventually erase even their footprints, because it churns the ground. They hilariously call that gardening. So that's the flag, and you can find a lot more cool pics if you go to this website here, LROC, and it's on the screen, and so if you need it, you can come back to the video and check it out. But very, very cool imagery that's come out of this spacecraft. All right, and besides the mare, there are craters on the moon as well. That's my favorite one, because its name is Theophilus. But there's also Aristoteles, Eudoxus, I can't say that right. Most of the craters got named for famous scientists, people of yore, philosophers. There's Plato and many. There's so many craters, you have to use up a lot of names. There's a nice listing of some of the bigger and smaller craters at about this phase. And this is also a wonderful, wonderful resource. If there are any teachers on the call here, this would be a great thing to show your students. This is actually a video, and it goes through the whole phase, lighting up all the craters as they come along the terminator, that line between day and night on the moon. And it's just a really fun resource. So there it was for last night, 19 February. And this can be found, this is at the SVS site, the Science Visualization Studio, which also has just tons of cool resources. These guys do an awesome job of taking data and making it something you can look at and grasp visually. That's really how humans learn. We like to see patterns. We like to see data put in. We don't see numbers well. But when you color it and make it pretty and make it cool, then we can get it. So there's a lot of tremendously cool visualizations at this site. All right, and that is all for now. So I'm going to stop sharing and come back to Heather here. Heather's turning her camera back on. There we go.
So someone was selling Girl Scout cookies today, so I had to pop out really fast to excited about my newest friend in Memphis, Dr. Ann Viano. She is at Rhodes College, but tonight she's got some different information to share. And in the meantime, later, make a point to check out the observatory at Rhodes College.
All right, thank you very much. Unfortunately, I'm unable to get to the observatory tonight due to snow and ice, but I'm going to talk about something that I hope you'll find interesting. So let me share my screen here. hopefully you can see that. So I'm representing the college, of course, in Memphis, but I'm also a member of the Memphis Astronomical Society. You can find information about them at memphisastro.org. But I'm going to talk tonight about some constellations that you will find in the northern part of the sky, if you're here in the northern hemisphere. And these are constellations you've probably heard about for many years because they're very prominent for a couple of reasons. And so in the background here, you might see here to the right, Ursa Major, the big bear. I'll try to point this out. Here it is. Ursa Major, the big bear. And here we have Ursa Minor, the little bear. Down here we have Draco, the dragon. Here we have Cepheus, the king. Cassiopeia, his queen. And up here, Camelopardalis. So why are these constellations so familiar to us, for those of us who live in the northern hemisphere? It's because they're always visible to us. And so here we're looking at a view. I think this was taken from Oregon. This is a view looking towards the north. And as Dr. Teets talked about earlier, he said Polaris doesn't really move in the sky. Here we have a picture that's a time-lapse photo. So this spans many hours during the night. And the stars rotate around the pole star, Polaris. So these stars, if you could watch them move over the course of many hours, would be rotating counterclockwise around that pole star. And they would make one revolution in 24 hours. Now, we have the sun that comes up and kind of blots out the sky for 12 hours, so we can't watch it for a full 24 hours. But if you could, you would see these stars make one full revolution or rotation around the pole star, Polaris. And over here on the right, I was just trying to show you why Polaris is at this location when we're in the northern hemisphere. So this green circle represents your location. Sorry, I'm just reading the chat to see if there was a question. This green circle represents your location, and you can see there's a north, a south, a east, and a west. So if you were standing on the ground and you had a compass, it would point north, south, east, west. Polaris is located where this little blue mark is. It's above the northern horizon a certain number of degrees, and in fact, that number of degrees is equal to your latitude. So here in Memphis, we are at latitude 35. So if I want to see Polaris, I go outside and I look to the north, and I go up 35 degrees. That would be about the width of 3/5 up from the horizon. So here we see a couple of constellations. This is supposed to represent Orion. This one on the backside is representing the Big Dipper. At a certain time, a few hours later, these stars would have rotated, and they would rotate counterclockwise around that pole star, and the Big Dipper would be up almost overhead, not quite. Orion, however, would have gone below the horizon, and you wouldn't be able to see it. 12 hours later, the Big Dipper is low in the north, but it is still rotating around the pole star, so you can still see it. Orion is just rising, so you can barely see it. So there are certain constellations in a certain region of the sky that are always visible, sort of this red circle, or here in the sky, these circles that don't dip below the horizon. Those are called circumpolar stars, and the constellations that contain them are called circumpolar constellations because they never set below the horizon. So let's take a look at some of those constellations. So here I've drawn a yellow circle on a star map. So this map is as if you go outside and you face north. Here's the cardinal direction, your compass point. And if I go up about 35 degrees here in Memphis, there's this sort of prominent star, not particularly bright. This is Polaris, the pole stars. And we said that all the stars, they rotate counterclockwise around the pole star, and they go once around in 24 hours. And there are some constellations inside this circle that you probably know and maybe love, like I do. One of them is Cepheus here. It sort of looks like a square with a hat on or a house, but it's actually the king in his chair. Up above Cepheus, you have the constellation Cassiopeia. Some people call it a W or an M or a question mark, but it is Cassiopeia the queen sitting on her throne. Now, in Greek mythology, Cepheus and Cassiopeia were married, and their daughter was Andromeda. A little bit higher at this particular time, we have I have trouble pronouncing this one, Camelopardalis, which is a giraffe, believe it or not. And these pictures I'm showing you are just from a set of constellation cards that was published in London in the early 1800s. Just shows you that constellations have always drawn a lot of interest and awe from the public. We see Ursa Major here is a little bit cut off, but the asterism, the Big Dipper, some of it is a circumpolar asterism or stars. And then down below Ursa Minor, we have Draco, which is the dragon. And the dragon kind of wraps around between the Big Dipper and the Little Dipper, and it kind of wraps up around the Little Dipper or Ursa Minor. Okay, so let's look a little bit more closely at the Big Dipper, which is part of Ursa Major, the Big Bear, and Ursa Minor, which is sometimes called the Little Dipper. In the Western tradition, it is in fact a Big Bear and a Little Bear. But as we've heard earlier, so eloquently discussed by these other panelists, there are different star lore traditions, and different cultures have come up with different ways to represent these constellations. In the Ojibwe tradition, Ursa Minor, which we think of as the Little Dipper or the Little Bear, is actually a loon, which is a bird up in the northern part. So the Ojibwe were one of the largest Native American tribes in the northern part of the United States and into Canada. Ursa Major, which contains the Big Dipper, in their cultural tradition, this was a fisher, which is a small carnivorous mammal that you find in the northern part of the United States and up into Canada. It looks a little bit like a ferret. This is its tail, and it has 4 little legs. Heather can probably tell us more about fishers, but I think they're pretty interesting creatures. So let's go a little bit deeper and look at Ursa Major, and in fact we'll look at the Big Dipper and talk a little bit about the stars, because these are easy constellations to see. And if you have even a pair of binoculars, you can take a look at these constellations and you can note some really interesting features. There's some great things to observe. So here is the constellation Ursa Major, and it contains this asterism, the Big Dipper. And here are the stars of the Big Dipper. This is a beautiful image that I did not take. Unfortunately, this might be a Hubble picture or something. But the names of these stars are listed here in white. And we heard earlier that some of the names of stars are kind of difficult for us to pronounce here in the West because they come from the Arabic tradition. And I've decided just to talk a little bit about the distance to these different stars. And so the star that is the furthest one in the handle of the Dipper, Alkaid, is about 104 light years away. And that means that it takes light from that star 104 years to reach us here on Earth. So a light year is the distance that light travels in 1 year. And then we have 2 stars very close to each other, Alcor and Mizar. They're 80 light years away. Then we have Alioth, which is 82 light years away. And we can see the stars that make up the cup of the Big Dipper. They're all between 80 and maybe 120 light years away. And this is kind of unusual for a constellation. When we talk about a constellation, we're just talking about stars that are in the same region of the sky. They don't necessarily have to be at the same distance to be included in a constellation. But the Big Dipper here, this asterism, these stars are roughly all at the same distance from us, which makes it kind of unusual and kind of interesting. Now, these stars in the Big Dipper are very bright stars. Most of these stars are giant stars, which means that they're giving off a lot of energy. So even if they're far away, they're still bright in our sky. Most of these stars are giants. I think only one of them is actually a main sequence star, this one, which means it's kind of like our sun. It's converting hydrogen into helium. These other stars have moved on to other fuel processes, other nuclear reactions that make them puff up and become large giant stars, even supergiant stars. So they're very big, which makes them very luminous, which makes them very bright in our sky. There's some interesting things about this. Dr. Teets talked about how Polaris is a double star. It turns out Dubhe here is also a double star. One star is a giant star, one star is a main sequence star. And there's some talk about the star Alioth. People used to think it was a double star, but now the thinking is that there is a planet orbiting that star, and that is causing the fluctuations that we see in its brightness. Okay, now Dr. Teets already explained to us how to find Polaris, but I'll repeat it because it's probably one of the coolest things you can impress your friends with, that you can find the North Star. If you can find the Big Dipper, which is almost a circumpolar constellation or asterism, and you can find the two stars that make out the front of the cup. So here's the handle, and this is the cup. These two stars then will point you to Polaris, the pole star or the North Star. And then it's not particularly bright, but it should be visible to the naked eye. Even here in light polluted Memphis, we can just make out Polaris with the naked eye. And sometimes, if you're lucky, you'll be able to see the rest of the Little Dipper here. On the right here, I have a picture that I took. The last trip I took before the pandemic was to Tucson, Arizona, which is known for its beautiful dark skies. And I took a picture here. You can just make out the Big Dipper, and I think I even added something here. So here's the Big Dipper in the sky, and if this tree weren't here, we would be able to use the pointer stars and go over and find Polaris. And in the middle here, you can see some of the stars of Draco, the dragon, coming up between the two dippers. So there are a lot of neat things that you can observe by looking at these stars. Even a pair of binoculars will show you different colors, different brightnesses. Lastly, I'll just talk a little bit about the Little Dipper. So we've heard a lot about Polaris. We learned that it's a double star, it's even a triple star system. It's about 400 light years away. So the light, when you look at Polaris, that light has been traveling 400 years just to reach your eye, which is pretty amazing. But the other stars that make up the Little Dipper, you can see have slightly different colors, different brightnesses. These two stars are kind of wildly different in their distances. Kochab is 131 light years away, Faircad almost 500 light years away. So just because stars are close in the sky doesn't mean they're at a similar distance from the planet Earth. I think I'll stop there to see if there are any questions, and then I know we're eager to get on to part 2 of tonight's discussion.
No questions right at the moment, so, but lots of thanks. Heather, did you want to take it over?
Well, I think we're ready
There we go.
to... Sure. I think that we're ready to start again from Memphis, drive 7 hours up Interstate 40 onto 81 to see our friend Adam Vans in Kingsport, Tennessee. If you're just joining us, this is the Tennessee Virtual Star Party hosted by Warner Park Nature Center, as well as many of our partners. Thank you. The whole thing on YouTube. This is being recorded, and you'll be able to check it out later. So, Adam, what you going to talk about now?
Okay, thank you, Heather. Well, I'm going to try to stay warm because it's getting colder out here. But, well, I had to change some equipment around. You probably saw me disappear for a little bit earlier because I had to move the camera onto my telescope here. And I'm going to be looking at one of the bright stars that I mentioned earlier that's in the part of the winter hexagon, the star Castor. And the star is spelled, by the way, C-A-S-T-O-R, Castor. and it's paired with another star called Pollux, Pollux. They make the heads of Gemini the twins. So let me bring up, again, here is our nighttime sky like we talked about earlier. We see the entire sky. Do you remember the name of the space that's right over your head, which would be the center of this chart, starts with a Z. Can you remember the name that I mentioned earlier that you learned? And it's the name of a very old TV brand, Zenith. So it is the zenith, the point straight over your head. So that's the very center. If we just go a little bit to the lower left a little bit, you're going to see the pair of stars that makes Castor and Pollux, part of Gemini the twins, to the upper left of Orion the hunter, which is easily recognizable. Well, what are we looking at here? Now, I have a live view from my telescope right now, and this is Castor. There's a little bit of a coloring because of trying to get the focus just right, but they are blue stars, and you can see that there's two there very clearly. Now, there is some limitations with my telescope, but I don't know if you're going to see this. It's almost in between the double stars and where my head is, my video, that there is a very faint little dot there, almost halfway between me and those two stars, and that's actually the third main companion of Castor. So this is a live view, and I'm on a deck, and that's why the image is jumping around so much. But of this multi-star system. So how multi is it? First of all, there's Castor. Okay? So remember, just to the lower left center, and there's Castor. Right next to it is Pollux. That's the star we're looking at. And here is what we're really looking at. Okay, first of all, you see three stars, and it's the Castor star system. It's also the second brightest star of Gemini, so it's Beta Geminorum. Alpha would be Pollux, which is the brightest star. So first of all, the two stars you saw from my camera, from my telescope, that was a live view, that's right now. That's Castor A and B. And you see the color, blue stars, very hot. And so very hot stars are caused because they're very large stars. The bigger a star is, the more gravity it has and squishes the inside more so and generates more nuclear fusion. Therefore, it's brighter and hotter. Very simple. Those two stars are orbiting each other like a waltz where the two stars are going around each other, or two dancers going around each other. As a system, those two stars are orbiting the center of mass with that third star, Castor C, which is that fainter star that I pointed out that was, and I can tell that it's kind of reddish, and I don't know if you actually got to see it by the time it goes through Zoom and YouTube, but you see three stars there. Turns out each of these three stars is a double star. So there's actually 6 stars there. And so, that's kind of like, the icing on the cake of the story here is that Castor A is actually 2 stars, Castor B is 2 stars, Castor C is 2 stars. And so now you have 3 pairs of stars. The pairs of stars are orbiting each other, and therefore Castor A pair is is waltzing with Castor B pair of stars, and then all 4 of them together are in orbit with the Castor C pair of stars. So you actually have 6 stars here. We visually cannot see the pairs of stars. We have to use a spectrograph where we split the light into little rainbows, little spectra. And with that, we can see the overlapping of two spectra, and we can tell that there's actually two stars there, not just one. And so lots of neat things. But again, Castor A and B are blue-white stars. Let's go back. There's that live view. So this is a pretty accurate color. The jumping around is just because it's on the deck and I'm moving. But that shows that it's live. And so you can see that here we see Castor and Pollux. Now, I have another picture to show you that relates to this. And I brought this up a month ago with the previous live viewing, and it's stellar classification. I'm going to talk very quickly about this. The bigger the star is, remember, the more mass it has, therefore the more gravity. So it's squishing the center more, generating more nuclear fusion, which then generates more heat and light and energy. So the bigger the star, the brighter it is, the hotter it is, and the color tells us the temperature. Hot stars are O, white stars are not as hot. Those are A stars. G stars are yellow. There's a famous yellow star that we all know, and we see it every day. It's our sun, as an example. And then M stars are faint and red. Notice the letters. O, B, A, F, G, K, M. How do they get that listing? Well, I talked about this last time also, and it was thanks to Annie Jump Cannon and a number of other ladies who were hired as computers back in the beginning of the 20th century, where these people would measure stars and their brightness and look at their spectra and gather all this data manually. There was no physical mechanical computer back then. And so that's what they were called, and that's what they did. Well, Annie Cannon was so good that she took the original listing of how they organize the stars. Like, okay, all these stars, they all look the same, so we'll call them A. And then the next in this list, these are B's and these are C's. But they had no rhyme or reason to it. They were just a list. She took that original list, cleared it all up, and organized it by temperature and size and the spectra itself, and then finally made sense of it. So the stellar classification scheme is from her. And so rearranging that list made it this kind of a weird list. Instead of changing all of the original data that they gathered for years, they just kept the letter organization of O, B, A, F, G, K, M. Well, how can you remember that? Well, use a mnemonic. And a very popular one is O, B, A, fine gal or guy, kiss me. I'll say it again, O, B, A, fine gal, kiss me. So that's one way of remembering it. Here's my homework assignment to you for tonight. Make up one of your own. Write down these letters, O, B, A, F, G, K, M. Write them down. Make up a mnemonic of your own. I don't care how silly it is. The sillier the better. And send it in on the YouTube chat tonight. And hopefully Theo will see some of them, and by the end of this of our session here, we'll read some of them out. Be aware others will see what you're posting, and we will not read ones that we shouldn't be reading. But be kind, but be silly, be creative. O, B, A, F, G, K, M. How can you remember the order of those letters? By making up your own mnemonic and send it in on the YouTube chat. I'm going to stop and keep it a little shorter, and we will go back to the, go back to the group. Thank you.
Adam, I had a question for you. What kind of telescope do you have on that tonight?
Okay, I have a refractor. Hang on one sec. There we go. I have a refractor, telescope. That means it has lenses in the front, and it's more portable for me, because there's also telescopes that are big reflectors that have mirrors, and they can be really, really big. But those are actually your best bang for your buck. This refractor is very good at splitting double stars, great for planets, the moon, the sun with the proper solar filter. I cannot stress that enough. You've got to have the right thing and know what you're doing. If you don't even try. But the moon's great. But you can also use it on deep sky objects. Probably the real problem is I'm on a deck. And so the deck vibrates and jiggles and everything. I really should be on a solid surface for a better view. But that's how it is.
Yep. Rough size? 80 millimeters?
130 millimeter. Okay. It's a little over 5 inches in diameter. I'll say the brand. Normally I don't like to advertise, but it is an astrophysics telescope. So it's a very good telescope. So popular that I had to wait 9 years in order to order one. And now the list is longer. It's now about a dozen years to get your name called to actually buy one of these. So they're very popular, and they only make a small amount at a time.
And like any other handmade thing, if you have to ask what the price is, you probably don't want it. I'll
say this. It's actually less than other similar sized commercial telescopes that are not as good. And she is right. These are handmade. They do not leave their company until they are perfect. And they only make 100 at a time. And that 100 takes them approaching a year, almost a year to make 100. And they're made in is it Illinois?
It might be. I know we've got an astrophysics mount here around the house, so it might be.
Right. They're American made, if I can't remember the state correctly, but they are American made, and that's kind of unusual too, but it's great. These are excellent telescopes. So
I've got 2 takers on your homework here. Rebecca Love out of Memphis says our best astronauts finally got Kelvin measurements. And Bert and Kim Bailey says Orion buys art from groovy kaleidoscope makers.
So, those are excellent. Hopefully we'll have some more we'll save them for the end of our session. Were there any other questions? I didn't get any from last time, but I didn't know if there's any others.
I don't think so. I think that was it.
Okay. I'll give it back to Heather.
Well, I was going to mention before we head back to Heather, there were 2 questions that had popped in, and I think this is actually for Anne, but if she's not available at the moment. Can we see light from Ursa Major as of now in our lifetime?
That's an excellent question. So we talked about the distance to the stars in Ursa Major, and they are all, roughly 80-ish to 100 light years away. So that means it takes the light roughly 80 years to get here from those stars. So light given off the day you were born would reach Earth the day you turn 80 years old. So hopefully you live that long, and yes, you would be able to see that light in your lifetime.
And Dr. Viano, is there another equivalent to the North Star in the southern hemisphere?
Another excellent question, especially if you're a sailor. So we talked about how Polaris is at the North Celestial Pole. It doesn't move in the sky. It's always visible. And navigation on the seas, in earlier times, sailors used the North Star to navigate. They could figure out their latitude by measuring the altitude of the North Star. However, in the southern hemisphere, there is a constellation that is close to the southern celestial pole, and that's called the Southern Cross. It's not something we can see here in Memphis or in Tennessee. You would have to be below the equator, south of the equator, in order to see the Southern Cross. but it is close enough to the southern pole that you could use it for navigation.
Nice. All right, Heather, I think that was all the questions we had. Sorry, I didn't mean to steal the show there.
Heather, there you are. Okay.
No, this is a collaboration.
All right.
Yeah, this is a collaboration. So I'm just glad that everybody. Adam, do you have any events coming up on the mountain that you would like to share?
Good question. Not right now. We don't. We're close. The park is open, and you can enjoy. We have 3,650 acres, so we slightly beat out the Warner Parks, but you can still enjoy the outdoors, do the trails, see the animal habitats, but not a whole lot at this point astronomy related, just because it's very much close knit and contact. The planetarium theater itself is actually was and still is closed for the virus, but also we are refurbishing our theater. We're going through some renovations, so we're replacing the digital projectors because they're a dozen years old, and you don't expect your computer or TV to last forever either. So they're being replaced, and our star projector is being worked on as well. And to kind of exemplify the difficulty of what's going on, and I'll stop after this, is the star projector and the equipment we use in our planetarium theater is from Carl Zeiss, which is from Germany. They can't come to the States. They're not allowed. And their country is in they're in a lockdown. And so their U.S. counterpart that works with them, but in the United States, came and actually took all of our optics from the star projector and some other electronics and shipped them to Germany for them to work on. And then when they're done, they're going to ship it back. And they're hoping that they can come and do our installation, but they're having to talk to the American consulate in order to even see if they can even come or not. Otherwise, the U.S. counterparts will be doing that work. But lots of unusual difficulties and roadblocks, but we're like everybody else, we're being flexible, we're working with it, and we're going to end up with an awesome theater, an amazing theater, really. Actually, the only one like it in the Western Hemisphere. That's how unusual. And it's going to be worth seeing when we're able to and safely. So good things come to those that wait. So, but as far as like sessions or observing sessions or anything, not at this time. So I'm going to stop, give it back to Heather.
I think she says Billy can just go ahead and
Oh. Okay, sorry, I'm just sitting here like I don't have any place to go. Alrighty, let's see. Just to kind of follow in Adam's footsteps, I just want to mention a couple of things that we've got going on virtually at Dyer Observatory. So I'm going to start my screen sharing here. Give me 1 second. Let's see. Share screen, and there we go. All right, so we've got a talk coming up this week. We're not going to be in person at the Dyer Observatory. Oops, hold on, sorry. Hold on, I got too many transitions here. There we go. So Dr. Stephen Taylor of the Physics and Astronomy Department at Vanderbilt is going to be doing a talk on detecting gravitational waves. So check out our homepage for that. And also on our homepage, we have a couple of star charts that are free for download. There's a black and white one that's good for printing, and there's a color one which looks great on the screen. So you can check those out and see some of the things that we've been showing tonight. And then also on our homepage, and you can see our address there, we have a nice celestial calendar that we put together for February. We have one in March coming up. So lots of information on that, and again, free for downloads. Be sure to forward the links and tell your friends about it. All of the events that we're doing virtually are free, so you can go to our homepage and you'll see links to YouTubes and things like that to access the virtual sessions. And then, of course, we've got resources like the star charts and the celestial calendar that are also listed on the front page for download. So be sure to check those out, and if you have a question, you can always email us. So let me stop my share there. Alrighty, so we've done a good amount of observing. We've been talking about what's up in the sky. We've been talking about stars orbiting around one another. So let's talk a little bit about some other things that orbit around one another, namely planets going around the sun. Now, instead of, let me scoot this down just a bit. So instead of us watching videos or trying to peer through a telescope and see a planet like Mars this evening, which I think Theo is going to be talking to us a little bit later about, we've got something a little bit different. So this, you've probably seen one of these before. It's basically a model of our solar system. We've got our sun here, and I'll give you a few different views of this in just a moment. But we have our planets around. This is known as an orrery, O-R-R-E-R-Y. So it actually gets its name for the fourth Duke of Orrery. I forget his true name, but the title that was held was fourth Duke of Orrery, which, if I remember correctly, was Irish in origin, but really gets its name for one of the first, or one of these that was really built for one of the nobility of Orrery. But anyway, this particular version that we've got here, I kind of scoot off to the side just a bit. This is one that has been 3D printed. So the Dyer Observatory is lucky enough to have a 3D printer available. And last year we actually, or was it, no, actually it was 2 years ago, we built this one. This is actually a design. It's not our own. This was a design that was put together by an engineer in the Netherlands, and he's actually set up a really nice Instructables page. I think his username is Dragonator, but we can put a link to the page that he's put together for this orrery. But if you have access to a 3D printer, maybe you're at a school that has access to a 3D printer, you can download all the files that the engineer has put together, and you can download this for free. And he's put together a really, well, I say he, maybe she, I'm not sure. We'll just say the engineer has put together a really nice page of the different parts that you'll need. There are a number of little bearings and other pieces like the brass tubing here that will be necessary in order to put this together. But there's a really nice page put together of the different things you have to get, even some links to where to get those things, and a really nice step-by-step instruction sheet of how to assemble it. So I've enjoyed putting this together and using it, and being able to then take it to use it for educational purposes. So, I tip my hat to the engineer who designed this, and thank them very much for making this all available to the public as well. But orreries, they're cool to look at. You can build your own. You don't have to have a 3D printer to build a type of orrery. You can make a very, very simple model just out of things from around the house. And that's especially useful for our younger viewers who are just starting to learn the names of the planets, the order of the planets from the sun, and how things go around them. This one is more kind of a more elaborate version. And so if you do put one of these together, especially this one, it'll take a little bit of time, but it is a fun project. So I'll give you some up-close views in just a moment, but this one is also battery-powered. So now you can see our little sun has lit up in the center, and I'll zoom in just a little bit. In fact, let me go ahead and do that now. I'm going to try to get us just a little closer view here. So now you can start to see what all's going on in here. There are a number of gears in this particular orrery. There is a rod that is actually traveling up through the entire apparatus and is connected to our sun here. And right below our sun is the main drive gear. And there's some really good videos online of this particular model. And you can see how the sun gear is then driving a gear, which drives yet another gear, to finally turn a gear that is connected to the planet Mercury that you see orbiting right here. Now Mercury, its gears are then connected to even more gears, which then drive the planet Venus. You see orbiting here. Then Venus, it drives the gear to turn to get the Earth orbiting, and even get our little moon going around our Earth there. But all of these gears are driving more and more of the planets until ultimately we get, and I'm going to turn this just a little bit here, ultimately till we get out to Neptune. So here we have Uranus, there we have Neptune. Now it may not look like Neptune is moving, but in fact it is. It's just poking along, just like it does in our solar system. One thing I do want to point out is that if you watch Mercury right now, see how it passes in front of the sun and blocks out a little bit of our sun. There it goes again. Actually, Venus did it as well there. But notice how it blocks out just a little bit of our sun. So that is the principle behind finding planets around other stars, or I should say one of the principles. It's called the transit method. So if we watch stars over a long period of time and we see them repeatedly dim just a little bit, that may be due to a planet passing between us and that star. So one other thing I want to point out here, and I'm going to zoom out again. So my camera is up just a little bit higher than the orrery, so I'm going to tilt my orrery back. All right. So now, what I want you to notice is that all the planets are running right through here. So you can basically see them all making, or they're all in one plane as viewed from the side. We don't have planets way up here or way down here. All the planets are basically going around the sun's equator, okay? Now, they're not all going around perfectly around the equator. Every planet's orbit is tilted a little bit with respect to the equator of the sun. But for the most part, they're pretty much going right around the sun's equator. Why do they do that? Well, as we look out into the universe and we start looking at areas that are forming stars, like the Orion Nebula, we can see stars in the process of forming, and they have disks of material around them. And those disks formed as a result of a cloud of gas and dust collapsing down and spinning up as they collapse down, and ultimately they flatten because of centripetal force and angular momentum conservation. That's a mouthful right there, but basically the forces at work in this rotating cloud as it's collapsing down because of gravity cause it to flatten out. And in the center of those clouds, those are where we find the forming stars. And then in the disks around those stars, that's where planets can possibly form. And that's what we think happened about 4.5 to 5 billion years ago for our solar system. Our whole solar system formed out of a big cloud that collapsed down. The sun had most of the mass at the center, but in that disk that was orbiting around the sun, the planets formed. And so as a result, we see them following that same path they had when they were in that disk of material still forming. So when you look out in the night sky, you look at where the sun travels through the sky, you look at where even the moon travels through the sky, you'll see the planets going through there as well. Okay? And that's again as a result of how our solar system formed. Now I'm going to fade the camera out for just a moment, and then I'm going to change our viewpoint. So instead of seeing from the side, we're then going to be looking kind of straight down onto our orrery. So give me 1 second. I'm going to fade out for just a moment. Okay, so now we've got more of a straight down view of our orrery. And plug it back in there. All right, so now we can see more of our top-down view and see how things are actually moving around. In fact, I'm going to zoom out just a little bit more here so we can see all of our planets. All right, so one thing that you'll notice is that our planets are all orbiting counterclockwise as we view from above the solar system. And again, that's a consequence of how our solar system formed. The cloud of gas and dust was collapsing down and rotating, and it happened to be rotating in this direction. So the planets formed and continued on that direction. Now I'm going to zoom in just a bit here, so we can get a little bit closer view of the inner solar system and a little bit better view of the workings of this particular orrery. Adjust our camera view just a bit there. All right, so one thing that you'll notice is that our sun, I think that you can see it, I'm trying to turn down the exposure. You'll notice that our sun is indeed rotating, okay? And that's a consequence of the way this orrery is set up, but our sun does indeed rotate. So it was part of that rotating cloud, and so it continues to rotate to this day. The top or the poles of our sun rotate a little bit slower than the equator of our sun because our sun is a big ball of gas. Now you also notice if I hold the camera very still, you'll notice that the sun is kind of wobbling around just a little bit. So that wasn't part of the design and it was not intentional. It's just I couldn't get the sun to set perfectly center where I needed it. But that brings up another really good point of how our sun actually rotates. If we could very carefully watch our sun, so if we were floating above our sun and we watched it over the course of a few years, we would indeed see that it wobbles around. And that's because even though its gravity is holding the planets in their orbits around the sun, the planets have their own gravity and they're tugging on the sun as they go around it. Now the planet that does most of that tugging is the big guy right here. So that's Jupiter. It's about 1/1000th of the mass of the sun. But Jupiter has more mass than all of these other planets and their moons and all the asteroids combined. I'm going to zoom back in just a little bit, just where you can get another view of those gears moving around. But this orrery is not going to be able to represent the sizes of our objects accurately. If our Earth was actually this big, then the little sun here would be about the size of a large beach ball. That would make for a pretty big orrery. And if our sun were this big, the Earth actually would not be in the room that I'm standing in now. It would be a number of feet away from me. So our orrery would be humongous. But what is very accurately depicted by this particular orrery design is the motions of the planets. Notice how the planets that are closer in, like Mercury, it's really whipping around the sun. In fact, if you time it, our orrery takes about 5 seconds for Mercury to orbit around just once. Earth, on the other hand, takes about 20 seconds. Mars takes even longer. Jupiter takes even longer. So the farther out you go in our solar system, the slower objects are moving and the bigger the orbits they have, which ultimately means that the farther an object is from our sun, the longer it's going to take it to go around. So Mercury only takes about 3 Earth months to go around the sun. Jupiter, on the other hand, takes about 12 Earth years to go around the sun. And then Neptune, zoom way out here, which way over here, it is indeed moving, but it takes it about 165 years to go around the sun. So our Earth takes 20 seconds in this model, but Neptune over here would take about 55 minutes. It's actually moving at about the same speed as the minute hand on a clock. And then the final thing that I'll point out, one thing that the engineer designed in this particular model is if you look at this big gear here, which is what is used to rotate our moon around our Earth, there are little marks on there. There are 12 of those. So that means if the Earth goes from one mark to another mark, that's representing 1 month of time. If you look at how the moon is orbiting around, it keeps getting about the same position in between each of those marks. It's because the moon takes approximately 1 month to orbit our Earth. It's not quite a month, a little bit less than that. But one thing that is really nice about this orrery is that, well, first of all, it looks pretty cool with all the gears that you see here. But it very accurately depicts the true motions of the planets. So with that, I'm going to fade back out right quick and change our view. You can probably hear the little motor there. Alright, and then fade back in. Alright, so do we have any questions about the orrery, or any questions in general, we'll say? I'm going to turn this guy off because it's kind of hard to hear over the little motor there.
I think someone would like to have the link to the Instructables.
Yes, I think what we'll probably have to do is put that link in the description of the video. But I think that if you just search Instructables and 3D Printed Orrery, O-R-R-E-R-Y, that should come up. And you'll see pictures of it. It looks very, very similar to this. I think the color is slightly different, but we can definitely put that link in the video description, I think. All right, well, it doesn't look like we have any questions, but if y'all think of anything, please post it. We can always answer later. So I'm going to turn back over to Heather.
Hey, Billy, can you hear me?
Yes.
I can.
Hey, Billy, great. What well, I guess back in December with the planets kind of aligning and all of these planets up at the same time in the western sky. Mm-hmm. When can we expect something like that again?
So yes, back in December we had something called the Great Conjunction, and that's where we have two planets in particular, Jupiter and Saturn, from our viewpoint, getting very, very close to one another in the sky. In fact, it was the closest that we saw them approach one another, at least where we could see them easily in the morning or the evening sky. It was about 800 years prior to last December was the last time we could actually see these guys very close together in our sky. Because of how long it takes each of these planets to orbit, so Jupiter's about 12 years, Saturn's about 30 years, every 20 years, we see these two planets meet up in our sky. But remember, each of those planets has their own orbital tilt. So every time they meet up, they're not going to meet up exactly the same way that we saw before. So in 2040, the next one of these great conjunctions, they'll be pretty close together, but it won't be near as close as what we saw in last December. They'll be, I think next time it'll be about 4 full moon widths from one another in the sky. So still decently close, but nowhere near as close as we saw. In 2080, we happen to have another one of these conjunctions that is super, super close. In fact, it'll be pretty much, or I should say almost identical to what we saw this past December. But you'll have to get up early in the morning to see them, because when they have that great conjunction in 2080, it's going to be, I think it's actually March 14th or 15th of 2080, but you'll have to get up in the early morning because there'll be early morning planets during that period. But you'll see them very close together in the sky again. And then I think it's something like 400 or so years before they get that close together again. But again, every 20 years, they'll get close to one another in the sky. It's just every now and then, the way their orbits align and where we are in our orbit, they appear super, super close. Now, when I say they appear super close, it doesn't matter when we see them close together in the sky, they are still hundreds of millions of miles apart from one another. It's just our viewing perspective makes it look like they're really, really close. let's see. I think there was another question. Is there a true scale model of our solar system on display anywhere? There are, I forget exactly where, but I've come across a number of models where it's not like this, where you've got everything together on one object, but they're basically a walking model of the solar system. And we often do this with some of our field trip students that come up to the observatory when they can actually come up. We'll have what we use is an 8-inch ball to represent the sun. Then we say, okay, if this is our sun, I want you all to then go to the first planet. First of all, you got to figure out how far that planet would be if the sun is this big. And it's amazing how far it actually is. Everybody usually comes up way short. And, they walk a couple steps when it's like, walk about 10, 11 steps. And then you say, okay, you're at the planet's position. How big would that planet be? For our 8-inch ball, Mercury is about the size of a period at the end of a sentence. It's truly kind of mind-blowing to see just how small these planets are compared to our sun. And then you basically walk along to those different positions. And there are museums and outdoor exhibits, I'm sure throughout the U.S., where you can walk to each of these planets and see just how big each of those are. So
We have one.
Oh, there you go. Well, please tell us more about it, Heather.
The Nature Center in 2006, a Girl Scout troop worked closely with Barnard Safer Astronomical Society to put in a Guy Atwell model. The Earth is a peppercorn, and you can start at Warner Park Nature Center and walk all the way down to the end of our entrance drive, which ironically is where Uranus is. Turn and walk all the way back up to the Nature Center and visit all 9 planets. And I am going to stick with 9 planets there, okay? You can also download the brochure that goes with that walk anytime at the Nature Center, c.nashville.gov.
Right.
All right, Heather, you ready for me to do something? What do you want to do?
I think I'm going to try this. Does that sound good?
Okay, share your screen. I've got the audio kind of on ready here, so you're doing the toads are first, right? Okay.
The toads are first. Oh my goodness, friends. It is such an exciting time outside. It really, really is. There's so much going on. There's so many animals to see. There's just, oh my goodness. There's so much going on. You go to the pond right now at the Nature Center, snow, and you think, nothing's going on. It's February 20th, for Pete's sake. But let me tell you, my friend Kim Bailey says that the magical courtship recipe is a February night at dusk, right around 35 to 45 degrees, and a gentle rain. And guys, guess what's happening tomorrow night? You are going to be able to experience this. Go to a pond, go to a park near you if it's safe, and check this out, because you are going to be able to hear the American toad. I don't care where you are in Tennessee, this is going to be happening. The American toad is about this, and it sounds just like this.
2 seconds. It'll load. It'll load. Oh, jeez. It loaded there.
And I can make the sound myself.
There you go.
Thank you. Theo. So you might have already been hearing that sound. I know my friend in Memphis, Charity, has already been hearing chorus frogs and spring peepers. So this is the time, y'all. It is amphibian time. They are doing this. They are calling for this. It's called amplexus in amphibians. This is a male and a female toad, American toad. And they're doing that for this, for eggs. They're going to lay hundreds of thousands of eggs in the pond at Warner Park Nature Center. And then from that, we're going to have hundreds of tadpoles. They look like Beth Harwell used to describe them as a watermelon seed with a tail. And they're all swimming around the pond. And those are going to emerge in June as toadlets that would actually fit on your pinky fingernail. Now, our next animal to talk about, you're really going to like that, is this guy. These guys are really active in February. This is kind of the iconic bird of Warner Park in Nashville. Many people see these hiking on a February pretty day, out in the day, even though we're thinking of most of these animals as being winter nocturnal animals. This is the barred owl, B-A-R-R-E-D. The barred owl has bars across his chest, and he makes a call that sounds like, who cooks for you? Who cooks for you all? Theo, can you help me out? Thank you. Guys, these are things that you can hear off of your back deck right now. That's why we wanted to stop the astronomy for 2 seconds, because you're out listening, looking at the stars, and you may hear some coyotes. I was hiking on the Hill Forest State Natural Area just 2 weeks ago with Melissa Donahue, and we heard some coyotes start up. It was like 1 o'clock in the afternoon. It was insane. And all I could think about was, can I outrun Melissa? No, you don't have to worry about that. They're not interested in us. But I do have a recording of some coyotes, and you might hear them where you live in Tennessee. Theo?
There you go.
Thank you so much, Theo. Another animal that I didn't mention that is going to be perfect tomorrow night, if you can find a good edge, so a place where the forest and the tall grass meet some mowed grass at dusk, look for a woodcock, W-O-O-D-C-O-C-K, woodcock. It's a bird, and see if you can catch it doing its sky dance. Google that later. Thanks a lot, guys, for allowing me to share my screen for Theo.
Whoop. And I think she might have got booted again. Maybe not. Anyway, so that was cool, and I hear all that stuff when I'm outside here because we've got a pond nearby and all that good stuff. So I might be outside looking at the stars, but I'm also hearing an awful lot of wildlife. What I told Heather earlier is I wish skunks made a sound because they don't, and they sneak up on you. I had one almost run over my toes. They just literally don't even know or care that you're there because they're skunks and nobody's going to bother them. All right, so let's see if I can get a screen share going, and then I'm going to have to bump past. I had these up as slides for reasons, and I know I have to wait for it, so I don't want to bump too fast. Oh, come on. Come on, you can do it. I'm surprised the system hasn't crashed and burned yet. But anyway, what we're going to do as soon as we can get to the appropriate slide, let me just escape out of this. Might be easier to do it the way Heather was doing it, actually. Because we're going to go... Here we go. It is easier to do it this way. Here we go. And the woodcock is pretty fun. You definitely need to do that. All right, here we go. So we're going to talk a little bit about the planet Mars. It's a long way now off opposition, which was in early October. But it's making some cool friends in the night sky right now. So Adam was talking about Orion and some of the bright stars there. So last night in particular, we had the Moon and Mars, which is dim but still noticeably red, and the Pleiades, the seven sisters. And since the Pleiades in the sky is fairly close to the ecliptic, the line that all the planets and the Moon and Sun tend to ride along, from time to time as the planets move, they get little photo opportunities with the Pleiades. So over the next few nights, the Mars is going to move closer until it's going to make a pretty nice, pretty picture. And it's something that a lot of times amateur astronomers enjoy doing, right? It's fun to catch a planet along with something else interesting in the sky. So we'll be looking for the Mars to look by the Pleiades here. Known popularly as the Seven Sisters, but I always liked the Pleiades because everybody who can see them in the sky around the planet had a name for that group of stars. It just stands out. And you know one of the other names because it comes from another culture that built cars. There are cars that have a circle right on the front with a group of stars in that circle. Subaru is the Japanese word for the Pleiades. But just like the North Star, they've been used as navigation and time markers for a very, very long time. Group of 7 hot young stars. Beautiful in the telescope. It's one of my favorite things to show at a star party. But Mars has been in the news, and let's flip. That was last night. This is tonight if you step outside. The moon's, of course, moving along in its way, so they're more in line tonight, but there's still Mars, the Pleiades, and the moon. And let's see. Oh, that didn't get stuck in. Okay. Every now and then you hear about the Mars getting really, really big, and it does get bigger when we lap it every 2 years or so in its orbit, but not that big, right? This is the Moon and Mars together in the sky, and yeah, Mars is just not very big. But we noticed those things that look like stars, but they're not stars, and we knew they weren't stars because they wander. Orion is always Orion. The belt stars don't go wandering off somewhere, but the planets do. They wander between the stars along that line that, again, the Sun and Moon also travel, which is the plane of the solar system that you could see in Billy's orrery. And some of them do something fun like this. They appear to turn around, they kind of stop, they go backwards for a little while, and then they pull forwards again. And that kind of motion was difficult to explain if everything was going around the Earth. It's a whole lot easier when you realize that we're all going around the Sun, and periodically when we catch up to planets, we start seeing that kind of a slewing motion. It's just an artifact of the geometry. Mars, though, gets bigger and smaller because we're either really close to it as we pass it by, or we're all the way on the other side of the Sun. So it does make a difference to your view where we are. It also makes a difference when you want to go there, because it's a whole lot closer when we're passing by than when we're on the other side of the solar system. That is a pretty decent view. I was fairly proud of that from earlier this summer, well, from October, when it was fairly close to opposition. And that's not greatly different than what you could see through the telescope at, some decently high magnification. Why do we like Mars so much? What makes it interesting? It's not quite as big as the Earth, but the fun thing is it's got as much land area as the Earth because there just aren't any oceans there. And we noticed early on that it had polar ice caps that grow and shrink with the seasons. So that kind of looks like Earth. Occasionally we see clouds. And so it reminded us a lot of our planet. And I think even if you were there, well, you'd say, well, this looks like, Arizona without any cacti whatsoever. So it does remind us of Earth. It's kind of sort of Earth-like, although there are some pretty major differences that we'll talk about here in just a bit. Okay, let's see if I can go back, because this works a whole lot better. Well, no, we'll just move along. So I used to say, people used to worry about Mars being invaded, okay? Or rather, Mars invading us. We had the War of the Worlds when we scared half the United States into thinking that, we were definitely going to invade. But instead, we have sent quite a large number now of orbiters and landers, and this is not an exhaustive list either, to Mars. So right now it's the planet that we know that's inhabited entirely by robots. Is there life there? Was there life there? That's one of the questions we're trying to answer with the newest member of the group down here in the corner of the Perseverance rover that just landed successfully on Thursday. So we've landed a bunch of stuff at all different locations on the planet. So you can see there where Viking landed, where Pathfinder landed. We'll spin around a little bit here and dot in a few of the others. Phoenix way up near the North Pole. There's Spirit, Curiosity, Viking 2, and we're going to pull out and see some of the many, many orbiters that are going around Mars. The one we really need to send next is some kind of a broadband transmission system, because it's tough to get images back from Mars in a really timely manner. But we have a lot of assets right now at Mars. What's Mars really like? Well, here's a good example. The top is the temperature in Los Angeles, how it goes with the seasons. And that's the range from high to low every day. Here's what it is in Gale Crater, where Curiosity is. So it is colder and the range is huge. Mars is like a desert on steroids. It'll warm up, sometimes even to freezing during the day, but then it'll drop way, way off at night. There's just no atmosphere to hold in the heat whatsoever. So Mars today is pretty cold and pretty dry. These dust devils are so huge that we can see those from orbit. They leave cute little tracks and shadows along the ground. They can be from a half mile to 12 miles high. That would be an astounding thing to see. They're not particularly dangerous because 5 air molecules hitting you is just 5 air molecules, and there's just no air really there much. So where we're headed now is this is a false color image to show the different kinds of minerals again that are there. But this is a really cool side of a crater, Jezero crater on Mars, and that looks, if it were on planet Earth, you would have no question, you'd say this is a delta formed by a river that emptied into this crater. And so rivers carry sediment, stuff. It's a great place, we think, to look for evidence of past life. So the rover put down not too far, right about here on the edge of this dune field. We're probably going to have to drive around it because we don't like driving in dunes. You get stuck and there's nobody to haul you out on Mars. It's got a different suite of instruments, so it's not just Curiosity version 2. They actually sent some different stuff with it. And so it's got a new laser camera that's pretty cool. Bigger laser, more power. It has zoomable cameras on the mast. It's got an ultraviolet spectrometer there on the end of the arm, and also an X-ray spectrometer, and those things look for exactly what are the rocks made out of. A weather station, so we'll get weather reports here from Mars pretty shortly. Subsurface radar to penetrate down a little ways and see what's under our feet. and MOXIE, which is an experiment to see if we can produce oxygen from Martian CO2. So that's kind of a demonstration thing just to see how that works. And of course, we're carrying a tiny little helicopter as well, Ingenuity, and that's going to be a ton of fun to see how well that flies. I will give huge bonus points if they can land it. I used to coach Science Olympiad, and landing a helicopter or an airplane is one of the most fun things that almost never goes right. Not to say that sometimes, you know, when you have a passion and you've spent a lifetime and you have a couple of kids, that sometimes a little bit of it rubs off. So this is the Mastcam Z test bed team. They got a working version and put it through its paces. And this is Jim Bell. He put himself in the picture 3 times. But this right here is my daughter Danica. And so I'm just real proud that she got to spend a lot of time having some fun with Mars. She's in a very Martian place right now, which is Sioux Falls, South Dakota. We had some really cool new cameras. These are all the cameras that rode along on the descent. And so one of the most cool things is the movie that hopefully will come out on Monday. We also saw in this bottom video here, this is the rover coming down under parachute. This was Curiosity coming down, and this I think was Phoenix coming down, but we caught 3 times we've caught them coming down from one of the orbiters caught the picture. But this is just the stupidest, coolest picture ever. This is one of the frames they downloaded from a camera on the crane, on the sky crane, looking down as they cranked the rover down to the surface. That's not CGI, that's not the animation, that is what it looked like. And the images off those cameras when they come back to Earth, they're going to put that together into, I think, one of the most awesome movies that we've seen off of one of our spacecraft. This is just going to be fun. This is the first color high-def picture. This is still from the Hazard camera, but they popped the cover off and took a nice picture. Looks like the software that was supposed to select a nice flat place did a good job. Looks like a really good landing zone. You can explore Mars from the comfort of your home. There's a lot of cool online stuff, and in particular there's a nice set of maps where you can, this is an elevation map, they call it the MOLA map. So you can see the tall volcanoes there sticking up on the left. That very, very deep impact basin really stands out there. And you can see the northern hemisphere has got a lot of kind of flat, low-lying places that are suggestive to many people of where an ocean on Mars might have been, at least for a period of time. So you can explore these maps, you can change what you look at and explore the whole thing, zoom down, find particular locations. It's a really cool little website. So if you're interested, that's a really cool thing to do. Of course, the million-dollar question is always, when are we going to get actual boots on the ground? We don't know. Short answer. Check on the Starship progress at SpaceX. They'll probably be launching another variant pretty soon. They haven't yet perfected landing, so mostly those have ended kind of badly. Although, again, it looks like a giant science fair experiment, so it's kind of fun to watch and see how they do. But maybe someday. Not as soon as I would have hoped. But this is a fun piece of artwork to sort of suggest what our aspirations are. Here's the future astronaut. He is definitely leaning on the hood of his roadster there. And I don't know how he's going to drink that coffee in his spacesuit. Also, the coffee would be rapidly evaporating. But it's a nice thought anyway. Now, Mars, it's not going to be an easy place, but there is a tremendous amount of science to be done there. You know, a lot of times people ask the question, and I see this on the comments on Twitter, well, why are we spending all this money to go to this dry, dusty, very desolate place? And part of it is because it's there. Why do people do anything? Why did somebody go to the North Pole or climb Mount Everest? But secondly, it's because there's a lot of good science to be done. When you only have an example of one planet, there's only so much you can learn. it would be really helpful to have other planets to study, simply so that our knowledge of our own planet will be better. Nobody thinks weather prediction is perfect, but if we can look at how weather works on Mars, on Venus, we might learn things that then can feed back into our understanding of our own planet. So it's not just, wasted money or to satisfy our curiosity, but I think that's not a bad thing. I think since time immemorial, people have been walking out of wherever it was they lived and said, I wonder what's over the next hill, and then the next hill. And really the planets are just the farther hills. They're out there and we see them and we're interested to know what is there, what can we find out, what can we learn. So hopefully we'll get there in my lifetime. I used to tell my kids I would cheerfully retire to Mars, but I don't know that we're going to make it there quite that fast. So with that, I'm going to stop sharing and make sure I've got, all right. Got back here, and who's up next is Anne, I think. Heather, are you back?
Yeah, I never left.
Okay.
Hey, Theo,
Yes.
does BSAS have anything coming up?
Not for the public. It's possible that there could be some private distance to Messier marathon observing. The weather will have to get better, but not yet. We're kind of waiting on you guys, on our partners at Metro Parks. Most of us are kind of in the getting a little long in the tooth category, so we would really like to have our shots. And then we will feel happy about, going back out and seeing all those cute little kids and stuff again.
All right, Ann, it's all you.
All right, thank you very much. So to end this great event tonight, we're going to talk about some things that we will not be able to visit, and those are distant galaxies. So let me share a screen here. Hopefully you can all see that. So if I had been able to get to our observatory at the college tonight, we were going to look at a couple of galaxies with the big telescope, but unfortunately I can't get there. And so I just thought I'd show you a picture. This is our building at Rhodes College in Memphis. This is the Department of Physics, and we have, it looks like two domes, but we've had a renovation. We have one observatory on the roof, and then we have an observing deck where we can take smaller telescopes out, and we have a nice view of the southern sky. The background here, this does not represent the skies in Memphis. This has been artistically enhanced. We do not have dark skies like that and beautiful stars. But in the dome, we have a 20-inch reflecting telescope. It's a 20-inch plane wave. It looks similar to this one. And instead of an eyepiece on the back, we have a camera that looks something like this. And there's a filter wheel here. So we use this to take images of objects in the sky. And we use a wide field CCD camera because it can collect light for a long period of time, and that's how you get those beautiful images of these deep sky objects. So earlier I told you a little bit about these constellations. Here is Polaris, our North Star, and Ursa Minor, the Little Dipper. And then here we have Ursa Major, and here is the Big Dipper again. And I want to talk about a place sort of in between those two constellations. In this region of the sky, there is a cluster of galaxies. It's called the M81 Galactic Cluster. And it's a group of distant galaxies. They are about 12 million light years away. So we will never be able to go and visit these galaxies because even if we could travel at light speed, it would take us 12 million years to reach this location in the universe. This galactic cluster is part of the Virgo supercluster of galaxies. The Milky Way is part of a galactic cluster called the Local Group, and the Local Group is also part of the Virgo supercluster of galaxies. So we're going to zoom in a little bit, and in this cluster, the M81 galactic cluster, there are two very bright galaxies that we would have liked to look at tonight. One is called the Cigar Galaxy. It's also called Messier 182, so it's object 82 in the Messier catalog. The other is called Bode's Galaxy, and it's Messier object number 81. Bode's Galaxy is the largest galaxy in this M81 galactic cluster. And we're going to zoom in a little bit and look at each one of these galaxies. So here are some beautiful images of Bode's Galaxy. The one on the left was taken by the Hubble Space Telescope, and the one on the right was taken by the Spitzer Space Telescope. So on the left, we're seeing mostly visible light, some infrared light, and you can see that this is a beautiful spiral galaxy. It's called a grand design spiral galaxy. At the center, there's a very dense core, and then it's surrounded by these beautiful spiral arms of very bright stars. And then in between the spiral arms, we have lots of dusty material that just gives us this beautiful view. This galaxy, like I said, it's about 11 million, 12 million light years away. But from one edge of the disk to the other edge of the disk, it's about 90,000 light years. So if you were to get in your Millennium Falcon here and put it on light speed, it would take you 90,000 years to get to the other side of this galactic disk. So that is a really long time. I don't think we could possibly do that. So a spiral galaxy is basically like a frisbee, where we have these beautiful spiral arms are in the disk of the frisbee. And then at the center, there's sort of a smaller sphere at the center that might protrude out of the frisbee a little bit. And you see these spiral arms seem to have a lot of bright stars in them. They pop out really well. And in the Spitzer Space Telescope image, they're even more prominent because this image is taken in the infrared. So these are wavelengths of light that are longer than red. This is more heat instead of visible light. And when we see these kinds of signatures where there's lots of infrared radiation, that tells us that something is giving off a lot of energy in the infrared, a lot of heat energy. And we happen to know that that corresponds to star formation. So in these spiral arms is where there's a lot of stars forming in this galaxy. Now you might be wondering, what's at the center here? And at the center of Bode's galaxy, very similar to our Milky Way galaxy, is a supermassive black hole. So a supermassive black hole is a very, very dense amount of material, a dense region of space where you have a lot of mass in a very small volume. Gravity is very strong in the supermassive black hole. And the one in the center of Bode's galaxy is about 70 million times as massive as the sun. So that's a huge amount of mass crammed into a small amount of space. And that gives rise to all kinds of interesting effects that we could probably spend a whole nother session talking about. This supermassive black hole at the center of Bode's galaxy is about 15 times the mass of the supermassive black hole at the center of our Milky Way galaxy. So Bode's galaxy is a very large galaxy. It's a massive galaxy, which makes for a really nice object to see with a decent telescope. So I told you that we know there's star formation. So these spiral arms in these spiral galaxies are very bright. So why are the spiral arms so bright? And one theory that explains it is this idea that these are called spiral density waves. It's basically a traffic jam in the disk of a spiral galaxy. So here I've just drawn some dots, and they represent just dust particles. In the region of the spiral arm, the dust is a little bit denser. And in the disk of the galaxy, the stars are rotating around the supermassive black hole, and these stars will come towards the region where there's more gas and dust. It's like you're driving along I-40 and you run into a traffic jam on your way to Nashville, and there's a lot more cars around you than there were a couple of miles ago. So as these stars, which are swirling around in the galactic disk, encounter a denser region, they kind of jostle one another and they cause more stars to form. So stars form when dust and gas gets wiggled and the gravity and a star is formed. So stars will form when there's a lot of dust and gas, and then you need something to cause things to wiggle around a little bit. So as these stars move through this dense region, all kinds of stars are formed. And that means that some of those stars are the biggest, most massive and brightest stars that we have. These big blue type stars, O-type stars, and B-type stars. Those are very bright, massive, luminous stars. But then, if you're driving to Nashville and you get out of the traffic jam, so eventually these stars make their way out of the traffic jam. The only problem is that the most massive and most luminous stars, these big O-type stars, the blue, the B-type stars, they don't live long enough to make it out of the traffic jam. They burn their fuel fast, and they live fast and try hard, and they don't make it out of the spiral arm. So what we're left with is that the arms of the galaxy, they're denser regions, and that's where the star formation is occurring. So that's where we're getting the brightest material. These bright stars are glowing brightly, and they let us see these beautiful spiral arms. So I just took sort of a hodgepodge of different galaxies so that you can see in all of these different galaxies, we could clearly see where these big bright stars are. These are regions where stars are forming. So there are just 4 different galaxies. You see these big white bluish stars forming and giving the structure to these beautiful galaxies. Sometimes you'll have galaxies interacting and it'll give rise to a ring where stars are forming. So it's very bright because some of those stars are the brightest stars and they don't live very long. So they pretty much die right where they're born. So this would be a ring of star formation. This is probably 2 galaxies that have passed through one another, and that's given rise to this ring of star formation. So when we look at galaxies, we can clearly identify regions where stars are forming because we'll see these big, bright, luminous stars. All right, we'll quickly look at the other galaxy that I had hoped to show you tonight, and that is the Cigar Galaxy, or M82. Again, it's in the same cluster, so it's roughly at the same distance, about 12 million light years away. It's smaller than Bode's galaxy, about 37,000 light years across. And this is kind of an interesting galaxy because at first we didn't think it was a spiral galaxy. We thought it was just an irregular galaxy. There are different types of galaxies. The beautiful spiral galaxies like we just saw and like our Milky Way. And then there are elliptical galaxies, which are basically just kind of blobs of stars that don't have any structure to them. And then there are galaxies that don't fit in either category, and they're called irregular. And for a while it was thought that the Cigar Galaxy was an irregular galaxy. But recently there's been some evidence discovered that there are some spiral arms in this bluish region. So in this galaxy, it's as if we're looking at the Frisbee edge on, and this blue region is the disk of the Frisbee. Now, the Cigar Galaxy is very unique because it has these puffs of dust and gas that seem to be coming out of the center of the galaxy. And in this image from the Hubble Space Telescope, the red that you see is infrared radiation and hydrogen. And we know that these are regions where stars are forming because it's infrared radiation. So this galaxy is kind of unusual in that we don't see star formation in the disk as much as we see it sort of billowing out from the disk, kind of perpendicular to the disk. So this is sometimes called a starburst region, or it's just a star forming region. And it's very unusual to see these big puffs of winds sort of coming out of the center of the galaxy perpendicular to the disk. So you might wonder, well, where do they come from? Why do we get this unique feature? And the current thinking is that these structures, these big billowy clouds of dust and stars that are forming, are churned up from the magnetic field of the galaxy. The magnetic field gets disturbed because the Cigar Galaxy is interacting with the previous galaxy we looked at, Bode's galaxy. These galaxies are close enough in their cluster that there is a gravitational interaction between the two, and that can kind of stir things up and churn things around and give us kind of a unique looking galaxy that is just making stars like crazy. These stars aren't going to last forever. Eventually, this galaxy will run out of dust and gas, so stars will no longer be formed and things will quiet down. But right now, it makes for a pretty spectacular thing to see in the sky. So that's where I want to end. I hope in the future we can take you into the observatory and we can actually look at some of these things in real time.
That was very cool. I like the cigar galaxy myself. That's just fun.
Wow. Dr. Billy, you have been. Do we have any questions coming in, especially anything for Anne regarding the galaxies? Regarding cigars?
Doesn't look like we have anything at the moment.
Candy bars?
Let's see. I do see that we had at least one of the OBAF GKM mnemonics come in. That was, let's make sure I've got the right one here. Orion battles actual fiends grabbing kale muffins. It's another great one. I'm not seeing any other questions at the moment. One thing that I was going to mention, if I remember correctly, there was a supernova that occurred in the cigar galaxy a few years ago. I think you all will have to confirm that. But because that galaxy was close enough, and the supernova was bright enough, if you were in really dark skies and you had really good vision, it was actually possible to see that supernova with your own eye. I saw it through the telescope, but yeah, my vision wasn't that good and it wasn't in the dark enough skies. But can you all confirm that?
Yeah, I actually took a picture of that, and I'm disgusted because I took it a few nights before the official Discovery announcement. And
No.
so, yeah, it was one of those things where we'd been having some issues with the telescope, and Roy was out of town. I didn't have anything to do, so I said, you know what, it's a nice night. What to look at? It's spring. Let's look at M8182. So I took, an hour of images, went to bed, went to work, didn't think about it until a couple days later, Drew in the planetarium said, hey, did you hear that there's a supernova in? I'm going, oh, you got to be kidding me. And another BSAS member was actually doing a podcast like the night before or something, and they were looking at it and not seeing, unless you have a reference picture that you're using, you might not. So anyway, there's at least two of us locally, and probably who knows how many others, because it's so photographed, that are kicking ourselves because we discovered a supernova. And you're going, oh, but I sent it in because they were interested in pre-discovery, pre-announcement photographs. So it was fun, but yeah. Never go to bed without comparing your pictures again.
Well, I will forever, or from now on, always refer to that as Theo Supernova. So, you discovered it in my mind. But yeah, it doesn't look like we have any other questions. Lots of great comments, though, for all of our presenters.
Yep. Let's see. Our backs are for grilling, kicking mutants? That's a bit strange. But yeah. We'll have to see if any get sent in later. Rebecca said they have 2 more, but she didn't list them. Or maybe she was talking about those ones up above there, yeah. I don't know why kale got picked on, but it did. And, yeah, the animal sounds, people like that.
I cannot thank our partners enough for being here with us for these programs. We have university professors represented. We have real live planetarium astronomers represented. Thank you all so much for partnering with the Nature Center for especially BSAS and the Adventure Science Center for over 20 years. So thank you so much. Next time we can all get together and do this, and hopefully we can be looking at the real night sky, and I will have better internet. So thank you all so much. Please be looking in your snail mail for a special thank you from Warner Park Nature Center. I'd also like to thank for providing the Zoom platform so that we could do this. If anybody has anything else to add, this is the time to do it.
Just going to say it's always a pleasure to work with everyone on here, and we always love being able to reach out to everyone out there and try to educate and take questions. So it's always a treat for us as well. So thank you for including all of us.
All right. All right, well, I guess with that we can sign off and say good night and look for another one. I think Billy will be hosting the next one. We'll be looking forward to doing that. Hopefully spring will arrive and we'll have melted off the snow by then. So anyway, stay safe, and we'll see folks again. And thanks again, Heather, for having us all on.
Good night, everyone.